Welcome to The Explainer. Today, we're diving into one of nature's most powerful and, frankly, paradoxical forces. We're going to explore how rivers act as both the ultimate life support systems for human civilization and, at the exact same time, some of our most devastating natural hazards. It looks incredibly peaceful, doesn't it? For thousands of years, humans have looked at landscapes exactly like this and thought, yep, this is where we're building our lives. But as we'll see, living on the water's edge comes with a pretty massive catch. We're going to trace that entire journey today, from a river's life-giving gifts right through to its absolute devastation. To unpack all this, we're breaking this explainer down into 5 steps. The gift of rivers, the drainage basin system, reading river behavior, when rivers rebel, and finally, a deep dive case study on the Nile. Part 1. The gift of rivers and how water shapes and sustains civilization. Let's look at why humans have always flocked to rivers despite the obvious risks. The key term to lock in here is alluvium. When a river floods, it's not just dumping water everywhere. It's actually depositing this incredibly nutrient-rich mix of silt, clay, and sand right onto the floodplain. Alluvium is literally the secret ingredient behind the world's densest, most sustainable agricultural hubs. Without it, the massive crop yields we rely on in places like the Ganges Delta or the Mississippi floodplain just wouldn't happen. Then we have hydroelectric power, or HEP. When you've got a steep gradient and high discharge, basically a ton of water moving incredibly fast, you can build massive structures like the Hoover Dam or the Three Gorges Dam. The water rushes through, spins the turbines, and boom, a huge, reliable supply of electricity. And the best part? It's completely renewable with zero greenhouse gases. Moving right along to Part 2, the drainage basin system, where we'll look at the mechanics of water movement. To truly grasp how a river flips from a resource into a hazard, we have to understand exactly how water moves through its catchment area. It builds in a pretty straightforward sequence. Step 1, precipitation. Rain or snow falls in the basin. Step 2 is interception, where vegetation actually catches some of that water before it even hits the dirt. In Step 3, the water that does make it down either infiltrates into the soil or it flows right over the top as surface runoff. Finally, Step 4. All that unintercepted, uninfiltrated water hits the river channel, pumping up its total discharge. You can really see the compounding effect here. The outer edge acts as the watershed. Inside, you've got these smaller rivers, tributaries, acting like a giant funnel. They gather up all that surface runoff we just mentioned and push it toward a confluence where they merge. Everything channels into the main river and out to the mouth. So you can easily picture how a huge storm across this whole area concentrates into one surging, massive volume of water in the main channel. Part 3. Reading river behavior, the heartbeat of a river. Now that the water is in the system, we need a scientific way to predict what it's going to do next. We need to be able to see the flood before it happens. Here's the core vocabulary for reading that behavior on a hydrograph. Peak discharge is the absolute maximum water volume. Lag time is the crucial delay between the heaviest rain and that peak discharge. The rising limb tracks how fast the river fills up, and the falling limb shows it returning to normal base flow. The huge takeaway here, if you see a short lag time combined with a really steep rising limb, you are looking at a very high risk of immediate danger. Think of this graph as a literal heartbeat monitor for a river. Check out that peak discharge curve. There's a horizontal line representing the physical capacity of the river channel itself. If that rising curve pushes the water volume above that capacity line, well, the water physically has nowhere else to go. It has to spill over the banks and wipe out the surrounding floodplain. Which brings us to Part 4, when rivers rebel. Let's dive into the causes and devastating impacts of flooding, which is driven by a messy mix of natural forces and human interference. It's absolutely vital to separate natural physical causes from human causes. Naturally, you've got prolonged monsoons, rapid spring snowmelt, steep valley slopes, and impermeable rock that stops water from soaking in. But humans, we're actively making it worse. We cut down forests, destroying that natural interception. We build sprawling concrete cities that skyrocket surface runoff. We even plow fields in ways that strip vegetation and severely compact the soil. These two setups perfectly contrast the problem. On one side, impermeable surfaces act like a brick wall, blocking water from soaking in and forcing 100% of it to just run off rapidly. But on the other side, natural tree cover acts like a sponge. Leaves intercept the rain, slowing it down, while roots let the water gently soak into the earth. When we replace those natural forests with impermeable concrete, we're essentially engineering our own disasters. And we have to ground this theory in human reality because the devastation is staggering. Take the 2010 Pakistan floods. That single event displaced 20 million people overnight and destroyed over 1.6 million homes. And it doesn't just stop when the rain stops. Floodwaters mix with sewage, creating an instant breeding ground for deadly waterborne diseases like cholera and typhoid. The economic and social fallout can last for years. Finally, Part 5. Case Study, the River Nile. Let's look at balancing survival and risk in Egypt to see how all this theory plays out in the real world. This is the ultimate trade-off. The Nile provides water for a massive 95% of Egypt's population in an otherwise harsh desert environment. But historically, its unpredictable floods wiped out crops and settlements. So humans intervened and built the massive Aswan High Dam. It provided incredible hydropower and finally controlled the floods. Problem solved, right? Well, not exactly. The dam also trapped that vital, nutrient-rich alluvium we talked about earlier. Now, downstream farms are starved of fertile sediment, triggering severe delta erosion and even international conflicts over water sharing. As we wrap up this explainer, I want to leave you with a fundamental question. How do we balance harnessing a river's incredible, life-giving power with surviving its inevitable, devastating wrath? Whether we rely on massive dams or simply plant more trees to increase interception, understanding this dual nature is absolutely key to our survival in a changing world. So, how will we manage our rivers next?